In the last video, I ran out of time before I got to the examples, so that's what I want to do in this video. And then we can be done with producer and consumer surplus. So suppose we have equations for our supply curve and our demand curve. Note that both of them are functions of Q, the quantity. So the supply as a function of quantity is Q squared over 72,000, and the demand as a function of quantity is 1100 minus Q divided by 100. I don't think either of these are all that realistic for supply and demand curves, but it'll make the numbers work out pretty nicely. Suppose you want to figure out the consumer surplus and the producer surplus. Well, what you need to do first is figure out the equilibrium quantity and price. You need to know what Q star and P star are if you're going to use all these different formulas. You got to think about when do these two curves intersect each other. Well, to figure out when two curves intersect each other, we can just set their equations equal to each other. We could say Q squared divided by 72,000 equals 1100 minus Q divided by 100. If I'm scared of fractions, I could multiply both sides of the equation by 72,000, and on the left, that would leave me with just a Q squared. And on the top, the 72,000 and the 100 would cancel out and leave me with an extra 720 up top. So I'd have 720 times the 1100 minus Q. This looks like a quadratic equation, so maybe it makes sense to get rid of all the parentheses and collect the terms on one side of the equation. Maybe I first get rid of the parentheses. I got Q squared equals 720 times 1,100. Well, let's see. 720 times 1,000 would be 720,000. And 720 times 100 would be 720 hundreds. And if I add these two together, I get 792,000. Sorry about the big numbers. Not only do I have to multiply the 720 and the 1100, I have to multiply the 720 and the negative Q to get negative 720Q. To solve this equation, maybe I add everything to one side to get Q squared plus 720Q minus 792,000. And that's all equal to 0. Trying to solve this equation is kind of a pain. I mean, realistically, what you'd probably do is Google it, use some quadratic solver to figure it out, or plug it into the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a. However, I can cheat a tiny bit. The way I can cheat is I happen to know that these two curves represent the curves that are pictured up here because I made this example. And I remember from when we were looking at this that the point of intersection is when Q is equal to 600. So I happen to know that one of the two solutions here will be 600, meaning Q minus 600 is one of the two factors. And if Q minus 600 is one of the two factors, there must be a Q here, so that Q times Q gives me the Q squared. And there must be a positive 1,320 here, because this negative 600Q and this positive 1,320Q have to net out to give me this 720. I could check my answer by taking this negative 600 and multiplying it by this 1,320 and making sure that I get 792,000. I think that works. The thousands come from these two zeros and this zero, and 6 times 132 gives me 792. Anyways, the point is this factors to this form. If this were ever on a test, you wouldn't see numbers like this. I'd make this even less realistic, and these would be like 2s and 3s and 4s so that you could factor and solve. But for the sake of this example, just trust me that this form factors like you see here. I got something times something equals 0, so either Q minus 600 equals 0 or Q plus 1,320 equals 0. So either Q is equal to 600 or Q is equal to negative 1,320. Remember, Q represents the equilibrium quantity, and it doesn't make sense to have that negative, so Q must be equal to 600. The equilibrium quantity, typically denoted with Q star, is this 600. And once I know Q star, I can figure out P star by taking that 600 and plugging it into either of these two equations. It doesn't matter which one, whichever one's easier for you to calculate. I don't love the idea of squaring 600, so maybe I won't plug into this top equation and I'll instead use this one. I'll take 1,100 and subtract 600 and then divide that answer by 100 and see what comes out. Let's see, 1,100 minus 600 is 500, and 500 divided by 100 is exactly 5. So P star must be equal to 5. Oh, right, that's exactly what I saw in this picture up here. What I'm trying to demonstrate here is if you have a function that represents supply and a function that represents demand, you can figure out the equilibrium quantity and then the equilibrium price by taking these two functions, setting them equal to each other, and then solving. And with these specific numbers, solving was a bit advanced for our class maybe. But trust that if this ever came up on a test, I'd make sure that the numbers were reasonable so that you could get the equilibrium quantity and then plug that back into either of these two equations, doesn't matter which one, to get the equilibrium price. Now that you know the equilibrium quantity and the equilibrium price, you can figure out the consumer surplus and the producer surplus. Let's do consumer surplus first. That's this area highlighted in pink here. You can memorize the formula if you want, or you can just kind of think about it's the area underneath the demand curve all the way down to the equilibrium price. So it's the integral from 0 to whatever Q star is equal to, in this case it'll be 600, of the demand curve D of Q minus the equilibrium price P star. This is a definite integral, so I put the dq at the end, not to be confused with this dq right here. The nice thing is we have values for all of these different symbols. We want the integral from 0 to q star. A minute ago we figured out q star was 600, so it's the definite integral from 0 to 600 of d of q. Our demand function was given to us right here. It's 1100 minus q divided by 100 minus P star, a number that we figured out up here, is equal to 5. This is the expression we'll need the antiderivative of because that's the definite integral that we want to evaluate, so we toss our dq at the end. Can you evaluate this definite integral? Absolutely you can. I'm going to take some time to rewrite it first, although you might be able to do this without even rewriting it. I'm going to think about this 5 as 500 divided by 100, because then I have 1100 minus q over 100 minus 500 over 100. So I can take the 1100 minus the 500, and I'm left with just 600 minus q divided by 100. You might be able to take the antiderivative of this to evaluate this definite integral just the way it's written, but in case you can't, instead of thinking about this as divided by 100, think about it as times 1 over 100, so that 1 over 100 is a constant that we can pull out in front of our integral symbol to change the integral that we need to evaluate into the definite integral from 0 to 600 of 600 minus q dq. I think we're finally ready to do a little bit of calculus. The antiderivative here is the antiderivative of a difference. So we just take the antiderivative of each term individually. The antiderivative of the 600 is 600q because q is our variable. And the antiderivative of this negative q, you might be thinking minus q squared, but it's not quite q squared because if you took the derivative of q squared, you'd bring a 2 down in front, and we don't want 2q, we just want q, so there must be a 1/2 right here. I don't need to tack on the plus c because I'm going to evaluate this thing from 0 to 600. The nice thing about evaluating this from 0 to 600 is when I plug in 0, 0 is going to come out. So really I just need to evaluate this thing at 600. When I evaluate it at 600, I get 600 times 600 minus 1/2 times 600 squared. If you really want to show your work, you could say you want that value minus what you get when you plug in 0, which is 0 minus 0, and then that difference gets multiplied by this 1 over 100. 600 times 600 is 36 with 4 zeros. In other words, 360,000. And from that, I want to subtract 1/2 times 600 squared, which is 600 times 600, which we said a minute ago was 360,000. And then 0 minus 0 is 0. When I'm subtracting 0, I'm not subtracting anything. So this definite integral evaluates to this. Half of 360,000 is 180,000. And 360,000 minus 180,000 is 180,000. So my final answer is 1/100th of 180,000. Cancel out these 2 zeros with 2 of these zeros, and I'm left with 18 and then 2 more zeros, in other words, 1,800. My consumer surplus is 1,800. Dollars technically would be the units that we're looking at here. But I'm not too worried about units. We'll just call this our answer. This represents the total amount of money that consumers saved, loosely speaking, when you compare what they actually paid for the product to what they would have paid theoretically for the product. We've gone this far, so we might as well calculate producer surplus, then we can call this good. Remember, for producer surplus, we're figuring out the area of this rectangle, and then we're subtracting the area underneath the supply curve, the area that's shaded in blue here. So we're again going to be evaluating a definite integral, and it's still going to go from 0 to q star, But now we want to start out with that green box, the area underneath the constant P star, and subtract from that the supply curve S of Q. We're evaluating a definite integral, so we tack on the dq at the end. This integral will give us our producer surplus. Much like the consumer surplus, we can plug in values for all of these different symbols. Q star is equal to 600, so it's the definite integral from 0 to 600 of P star is equal to 5, and our supply curve, the function is given up here as Q squared over 72,000. Evaluate this definite integral and we're done. There's lots of different ways you can evaluate this definite integral. One way is to think about it as two different integrals. The definite integral from 0 to 600 of the number 5 minus the definite integral from 0 to 600 of the quotient Q squared over 72,000. The reason you might want to write it this way is because this is a pretty easy integral to evaluate. And for this integral, I can think about this as 1 divided by 72,000 times Q squared. So I can pull that 72,000 out in front. I guess I'll write that all down. The integral from 0 to 600 of 5 dq minus 1 divided by 72,000 times the integral of Q squared dq. We've gotten to the point where we can use a little bit of calculus. The antiderivative of 5 with respect to the variable q is just 5q. And we're going to want to evaluate that from 0 to 600. And then from that, we want to subtract 1 divided by 72,000 times the antiderivative of q squared, which is 1/3 q cubed. But we need to evaluate that from 0 to 600 as well. I guess really I should have put the endpoints on my integral here to show that I want to evaluate that from 0 to 600. So what does this all evaluate to? I have no idea, but we can figure it out. This first one's pretty easy. We change all the q's into 600 and we get 5 times 600. And then from that we want to subtract what we get when we change all the q's into zeros. 5 times 0. The difference between 5 times 600 and 5 times 0 is just 5 times 600, which is 3,000. Over here on this side, I have 1 divided by 72,000 times 1/3 of 600 cubed minus 1/3 of 0 cubed. Nice thing about 0 cubed is it's just 0, and 1/3 of 0 is just 0. So this is going to be 1 divided by 72,000 times whatever 1/3 times 600 cubed is equal to. Let's see if this is arithmetic we can do in our head. I got 1 divided by 72,000. That's going to be a pain. I'll save that for later. Times 1/3, also kind of a pain. Maybe that'll help me out later. Times 600 cubed. Well, let's see. 600 cubed is 6 cubed times 100 cubed. And 6 cubed, 6 times 6 is 36. And 36 times 6 is 216. So I get 216 times 100 cubed. 100 cubed is 100 times 100 times 100. So I get 2 zeros for the first 100, 2 zeros for the next 100, and 2 zeros for the third 100. 216 million apparently is what this ends up being. Pretty absurdly large numbers. Fortunately, we'll be able to do some nice cancelization. The 3 zeros down in the denominator here will cancel with 3 zeros up here. So I have 1 over 72 times 1 over 3 times 216,000. You could try canceling out 216,000 in this 3 or something, and 216,000 in this 72. Either way will work, but it's a little bit easier if you recognize that 72 times 3 is 216, because 70 times 3 is 210, and 2 times 3 is the 6. So this times this is 1 over 216, and I'm multiplying that by 216,000. That's going to cancel, and I'm left with just 3,000 minus 1,000. In other words, 2,000. The producer surplus, in other words, the area that's shaded in brown here, is exactly $2,000 if you want to include units. We calculated a second ago that the consumer surplus was $1,800, that area shaded in pink. And yeah, that even kind of makes sense, right? Maybe you could see some symmetries here. It looks like the area in brown might be a tiny bit bigger than the area in pink because the area in brown is sort of curved in here. So yeah, I totally buy that this is $2,000 and this is $1,800. Once you calculate those values, there's lots of analysis that you might do in a business class, but for our purpose, in a math class, we're done once we get these two answers. What I want you to be able to do is calculate consumer surplus and producer surplus if I give you the equations of the supply and demand curves. And as long as you figured out how to do that in this video, you got everything that I'm trying to teach you.